Greeting everyone. This is Amr Hajumar. I'm the wireless market segment leader at Tektronix. Welcome to Tektronic Innovation Forum 2021. We're excited to talk to you guys about 5G and 6G technologies and trends. Um, I've been with tech for over 2 years. I come from semiconductors, where I spent over 10 years in R&D, starting from design, characterization, as well as silicon definition. So spent time with Texas Instruments all the way back from LTE, so the introduction of our smartphones, and also with Murata, Peregrine Semiconductors, working on switches for automotive radar at 77 gigahertz and 26 gigahertz. And I'll pass it to our DSP philosopher, Keith Tinsley.
Thank you for that introduction. My name is Keith Tinsley. I come from a background in radio communications and digital signal processing. I, likewise, have been here at Tech for about 2 years. I've done radio architecture network development for L3 Harris, and prior to that I was in wireless communication research and development at Intel Corporation. It's my pleasure to be here today with Don Delbro.
Hi all, I'm Don Delbro, RF Principal Engineer here at Tektronix. Unlike these rookies here, I've been here for like 35 years plus. So I have a pretty extensive RF background, been working in RF pretty much since the start of my career. Don't go as far back as Marconi, but not too far behind. So glad to be with you all here today, and hope we have some exciting demonstrations to show you on our new MSO oscilloscope.
All right. So the agenda we have for you today is we'll talk about some of the trends when it comes to applications and 5G innovation. And then we'll talk about problems worth solving around the beamformer that enables FR2 or millimeter wave technology. And then we'll talk about the solution that we're proposing today, which is a MIMO wide band analysis scope. And we'll top it with a demo talking about the over-the-air measurements, where Don will walk us through the setup along with Keith. So when we look at 5G applications and trends, there's many applications that 5G is enabling. The industry has been looking forward to enabling driverless cars, and the ability for ultra low latency is what's going to make that a reality. And the centerpiece that we're all depending on today in a pandemic is the user equipment or our smartphones, and users now are dependent on wide bandwidth to do videos similar to this virtual conference, but with wider bandwidth as we move from 5G to 6G. What that's going to enable is almost creating an avatar where we could all actually be in one room and have our images and be able to actually be alongside Don inside an aquatic chamber and see these demos. So that's what moving from one generation to the next generation has given us. So if we look at the ecosystem, and I'll focus mainly on the user equipment and the base station, in this case, we have the base station connected via optics to the backhaul to the data center or the cloud. And it's transmitting directly to the smartphone, as well as the CPE, which is the consumer premise equipment, similar to what I'm holding here in my hand. So this replaces the traditional Wi-Fi transceiver in our homes. Instead of connecting through cable, it'll be connected directly to the tower. One particular extra device that is included in the block diagram as an enabling FR2, which is millimeter wave band, is the beamformer. So what the beamformer allows you to do is to rotate or electronically steer without physically moving the antenna. And that allows us to compensate for the environmental as well as at high frequencies, these signals are easily blocked, whether by our hands or even environment, such as rain. So to get a better signal to noise ratio and throughput, electronic steering will allow you to actually lock the signal from your tower or base station to the actual phone, hence enabling better quality. And here, as a courtesy from our friends at Renaissance, who are leaders in beamformers, they have their 4x4 beamformers, which is controlling both phase and amplitude. But in this block diagram or in this evaluation board you see on the top, you could see actually an array of 16 of these beamformers, which are all 4x4, which are connected to 64 elements of a patch antenna. So there is definitely a need for multiple channels. So as you could see from this evaluation board, there is more than one point in order to evaluate and test the board. And as well here to the right, far right, you could see there's setup inside OTA, similar to where Don is located right now, and we'll show the demo. So what is the problem we're solving when we talk about beamformers? So the first pain point identified is mixed signals. So the ability to test both digital, analog, and RF. And the second pain point is to have multiple channels and a wider instantaneous bandwidth. So a traditional spectrum analyzer is tapped at 1 gigahertz of instantaneous bandwidth, and a MIMO, again, it's one channel, so it's limited to only one. And if we look to the right at this block diagram, you'll see 8 channels, which represents both vertical and horizontal, so 4 channels. And this 4x4 block diagram requires both a digital component or block. So it's a smart silicon that could program both the phase and amplitude of the signal that is being sent, hence electronically steering the beam. And Don will basically show us a demo of that. So in terms of testing, part of the specifications from the 3GPP requires us to, from the point of programming to the point that the signal is actually received, transmitted and received, we have to measure the latency. And in order to do that, you'll need a scope. But also, in order to test the different RF component and different channels, you'll need more than one channel. Hence, we're seeing this trend that is happening today when it comes to beamforming and MIMO to utilize a scope. And if we look at our solution for wireless 5G NR, we are proposing a signal view software with 5G features. So signal view is a software that Tektronix already supports various wireless communication standards such as LTE, Wi-Fi, Bluetooth, and we've added a new feature, which is 5G. And it's going to be released on our MSO 68B scope, as well as our SX 70,000 scopes. along with a AWG 70,000 arbitrary wave generator, which generates a true 5G signal. So the software features from SignalView allows us to do error vector magnitude, EVM, adjacent channel power ratio, ACPR, and spurious emission mask that we will be demonstrating. And some of our value proposition or benefits here is the ability to get a very attractive EVM of less than 1%, where we could look at 256 QAM, and we're already able to do 1024 QAM, which will be part of release 17. So the DMOD features we're using today is up to date with release 16, and we'll keep updating them as new releases come to market. So one thing that is of value for our customers is if you break down our portfolio in terms of field testing, IoT, EMI, which needs portability, reliability, both in the lab and in the field. We have the USB RSA, and they also support SignalView. So the same software will be able to work throughout our full platform. So it will also support applications that are less than sub 7 gigahertz. So you could use the RSA 5000, which goes up all the way up to 26.5 gigahertz, as well as the MSO that we mentioned, which could go all the way up to 10 gigahertz. And some of the unique features with the MSO as well is the ability to do instantaneous bandwidth due to the interleaving of our ADC up to 2 gigahertz. And we have a digital down converter behind each channel that allows us to have a separate path between the RF and the time domain. So Don will talk a little more about that. So the ability to also tackle or look at more than one channel, up to 8 channels. And finally, we have the SX scope, which covers the millimeter wave bands, less than 70 gigahertz. And it has very unique features such as the ability to correlate between channels, between various scopes. If you want to go up to 12 channels of 20 femtoseconds in terms of skew rate. With that, I'll pass it to Don to tell us a little more about the digital down converter and the IP we have around it. Don?
So as Amar mentioned, this digital down converter. So this is something new to oscilloscopes, maybe within the last 5 years or so. And first of all, as an RF engineer, I, in the past, very rarely used oscilloscopes. So this is something kind of new that really opens up the RF world to the oscilloscope, or opens up the RF person to the oscilloscope world, maybe I should have said. But if you look at the block diagram here, this shows a basic view of what we have here. And it's really 2 paths that are both feeding the same acquisition memory. So one path we would call the time domain path. That would be the top one. So we're going to signal condition, just amplitude adjustment depending on the input signal level. And then we're going to sample that at a very high sample rate. In the case of the MSO 68B, it's 50 gigasample per second. So normally in the in the time domain path, you're not always at full sample rate. It's going to change depending on the time span width that you have. So the wider it is, it's assumed that you're looking at slower signals. So there's decimation done so that it doesn't require so much memory. If you have a 50 gigasample per second, you're not going to be able to capture very much time before you've filled up your memory. So what's done is decimation down. But the drawback of that is when you decimate, now you've moved your Nyquist band down. So you don't have as much frequency range, or you're going to get aliasing. There's another problem there. So in the past, all you've had is this time domain path that then you could do an FFT on the data acquired. And the problem with that is it's very clunky, for one. And the bigger problem is that you can't independently control the time and the frequency domain. So you might want to see a wide span in your spectrum, but a narrower span in the time. Well, they conflict with each other. So you would have to, compromise between one and the other, or one would change when you didn't want it to. Not very useful. But having this digital down converter allows you to, in the spectrum domain, still sample at full sample rate, so 50 gigasample per second in this case, and then digitally down convert any 2 gigahertz chunk of bandwidth within the scope input range. So the MSO 68B is a 10 gigahertz oscilloscope, and you can place that 2 gigahertz analysis bandwidth anywhere within that 10 gigahertz, which is very useful, in particular that with 8 channels, each of them has independently a digital down converter, and each one can independently tune to a different center frequency as well as span. So effectively, you have 8 spectrum analyzers with 2 gigahertz bandwidth that can be positioned anywhere within the input bandwidth of the scope. And for things like MIMO that Amr was talking about earlier, this can be very useful. And we'll give you some reasons for that as we demonstrate that. But another thing I wanted to bring up is over on the right there's a table that's comparing specs between the oscilloscope and a spectrum analyzer. So normally you approach an RF guy with an oscilloscope, it's like, well, I can use that to check my digital bus or my power supplies or something, but not for RF measurements. But what I've highlighted in green here is where the scope is either at parity or better than the spectrum analyzer. So the one that really stood out to me is the DANL. That's like the fourth one down there. It stands for displayed average noise level. So basically the noise figure of the oscilloscope. And in this comparison, it was a full 10 dB better than the spectrum analyzer that I was looking at. Not something you might expect, but very important for these high order modulation signals that require a good signal to noise to get good modulation analysis. So that's a big plus for the oscilloscope, as well as having eight oscilloscopes or 8 spectrum analyzers in one to do multi-channel measurements. So there, having said that, there are a few drawbacks, in particular the spurious. In order to achieve that 50 gigasample per second, it's lower speed A to Ds that are interleaved in time together. And one of the results of that is you get interleave artifact spurs. That's just due to the gain, phase, and DC offset mismatches between all of the A to Ds. So we calibrate that out as well as we can, but there's always going to be some residual spurious left from that. So this is a little bit of a preview of the demo that we're going to be doing here. The picture shows it laid out on a table, but we've moved it into a anechoic chamber to get a bit more concise measurement results. But if you look below the picture there, that's a block diagram of our setup, and that's what we will be demonstrating here. So on the left is the transmit side. So we have our arbitrary waveform generator that's going to generate in this case, the picture says 2 gigahertz. We're actually going to move it to 3 gigahertz. So a 3 gigahertz IF signal. This will be a 5G signal. I have an uplink signal that's 100 megahertz wide, 256 QAM, and a 10 millisecond packet. So we're going to take that IF, send it to an up converter, and we're going to up convert it to 25 gig. And that's going to be sent to a beamformer, which is where we do the phase and amplitude adjustment. And then that beamformer feeds an antenna So in this case, I have a 4-element dipole linear array, just one that I built because I couldn't really find one that I could use with this particular beamformer since it's connectorized. Yeah, and that's another thing to mention here. In a lot of use cases, and like the pictures that Amr showed earlier, you're not going to have the ability to measure connectorized because the antenna is going to be integrated into that beamformer, so you don't really have access. Of course, when they're developing the IC, they can do whatever they want. They'll put it on a test board or something and then connectorize it out, which is what I have here, is one of the test boards. But, you know, if you had that case, of course, you could still use down converters to directly measure the beamformer amplitude and phase, which is a pretty good way to, you know, evaluate your beamformer right out of the box. But ultimately, you want to see how it performs with an antenna connected to it. So over on the receive side in this demonstration, we have 2 horn antennas. So we'll be looking at 2 receive antennas that are then going to take that 25 gig input in and then down converted back to 3 gigahertz that we started with. And then that's what we're going to measure on the oscilloscope. So if you look over to the right there, that's the oscilloscope displays. And we can see the far antenna in the picture is the yellow trace, and the near one is the green trace. And at this particular time, we're steered right down the middle between them. So the steered array is at 0 phase for both of them. So I'm trying to direct it right down the middle. And that can be a little tricky because you have to physically move it to dial it in. So you can see from the top one that the RF power is about equal. So you might know you're there. But the better way is to switch to a sine wave. And then that way you can match the phase and amplitude. So you'll know when you're directly steered right down the middle between those 2 antennas. So that's what I've done there on the lower right scope display. So with that, this is just a demonstration of the beam pattern of that 4-dipole antenna that was obtained by electronically steering to a single reference antenna. So the idea of this is typically when these antenna measurements are made on a beamformer, you may have noticed in one of Amr's earlier slides, there was like a gimbal. So they'll put the phased array in this gimbal, and then the whole device is rotated to a single reference antenna in order to obtain the beam pattern. So another way that might be considered doing it is to keep the reference antenna or antennas stationary and just electronically steer the beam. And over on the left there is what's shown when I've done that with a single reference antenna. So the problem with that is the beam pattern is going to change as you steer it. So that's the reason for wanting to rotate the device rather than steering it electronically. But if you had several reference antennas, say enough to fill out the 8 channels of this oscilloscope, you could have 8 reference antennas spread out in a semicircle, and then you could electronically steer it and obtain a beam pattern that looks very much like you would obtain by physically rotating the antenna. And there's some big advantages to that we'll talk about during the demonstration. But with that, let's go to the demo.
So what do we have here, Don?
Boy, big question. So what we're doing here is an over-the-air test of a beamformer.
Mm-hmm.
And this is for FR2 for 5G.
Okay, that's one of the 2 or 3 bands that are associated with 5G.
2 that I know of.
FR1 and FR2.
FR1, yeah, which would be sub 6 gigahertz.
And we're looking at the higher one.
Yeah, FR1 actually extends up to 7 gigahertz, and FR2 is like 24 to 50 gigahertz. About.
Oh, okay.
So in this case, we're going to be looking at 25 gigahertz signal.
Okay.
So let me describe the setup for you a little bit here. So we're generating the signal with the AWG, and this is going to be at IF. So by IF, this will be the intermediate frequency, because we're going to have to upconvert it to get to that 25 gigahertz.
Okay.
So from the AWG, we're producing in this case, a 3 gigahertz center frequency IF signal. And this signal is an uplink signal, which has a 10 millisecond packet and 100 megahertz bandwidth.
So we're mimicking the 5G OFDM waveform here out of the arbitrary waveform generator,
right.
AWG.
Right.
And then you're bringing that up IF and bringing it to RF and through the beamformer.
Right.
Okay.
So that's on the transmit side. So what we're showing here is we have the IQ, or actually the IF from that AWG. And that's then upconverted from 3 gig to 25 gig, sent to this beamformer, which is...
So what is a beamformer exactly?
So if you remember the old radar days, or maybe old military movies, they would show a dish that spins around. And the idea was that so that you could direct RF energy in a certain direction. But you would have to physically move the antenna all the way around. So when you're over here, you can't really see what's happening there. So what the military has been using for quite a while now, I'm not sure who discovered this, but it's pretty old technology. Is that if you take multiple antennas...
Probably is Marconi.
Yeah, it could be. That's a little bit too far back. But if you take multiple antennas and adjust the phase on each of them, you can effectively steer the beam much like you could by rotating a dish. The advantage of that is, like I said, you can, when you're physically steered here, you might not know what's going on here. But with a phased array, like is called here, you can steer that beam instantaneously wherever you want it to go. And if you have enough antennas, you can steer multiple beams to multiple places.
To cover that entire angle of attack.
So rather than having one big dish to rotate, they'll have several phased arrays so that you can cover the whole 360. There's usually 4 of them, front and back and left and right. And you can cover 360 degrees instantaneously, which is it's the big advantage.
That's excellent. So we've set up basically a base station type system in which we're giving OFDM input and being able to create steered beams.
Right.
Where are we steering to? So
then on the receive side, we have a couple of horn antennas to pick up that 25 gigahertz signal. Currently it's steered to this antenna, which is bore sight. So we're looking directly at the phased array with no phase adjustment on the phase array. So we're going to take that signal in and then down convert it back to the 3 gigahertz IF signal. And that's what we're going to send to the oscilloscope.
Oh, and that's that item that we have here.
So
it's covered
you
because
can't see it now because it's covered with foam. And there's a reason for that, because we're in a chamber here, as you can see, and you don't want the scope to be a reflective surface for the signals, because ultimately what we're going to try to do here is determine the beam pattern of that beamformer. The beam pattern being how well the energy is directed in the direction that you want it to go, and over what width of degrees that beam forms. So we have 2 of these antennas, but it is an 8-channel oscilloscope, so you could have as many as 8 of these on one oscilloscope, you know, patterned in a semicircular array here. I'm limited to 2, so that's what we'll be showing today. Yeah, that pretty much describes, one more thing. We have in addition to the over-the-air signal, there's a wired signal that's coming directly from the AWG to another scope. And the reason I like to do that, because this packeted signal, I need to be able to trigger on that. And if you're adjusting the beamformer, if you choose one antenna or the other to trigger on, you lose the trigger as you tune it.
Oh, I see.
So it helps to have a single stable signal that you can trigger on in this case.
But ultimately, our customers probably would have multiple beamformers from multiple input sources, or one input source, one beamformer. Or it just totally depends, correct?
Well, the beamformer itself usually has one input.
I see.
It's sent to several antennas, depending on how many. This particular beamformer has 8 channels.
I see.
I only have a 4-element antenna, though, so I'm only using 4 of those.
Mm-hmm.
Yeah, so let's talk a little bit how these things are tested. So what they're going to do is rotate this whole device here in order to obtain the beam pattern.
Mm-hmm.
So what they're going to do, if you notice the yellow trace there, you see it getting smaller. So we're going to measure the amplitude at each angle of degree here and then build out a plot of the amplitude versus the rotation degree. Right.
Mm-hmm.
So that can be kind of cumbersome. You can see with my setup here, I've got cables hanging all over the place, and probably every time I move this, things are changing, not just due to the rotation, but just the flexing of the cables and such. So boy, if you could do this without having to rotate the antenna, that would be a really big plus here.
Mm-hmm.
Not only because you don't have the cables flexing, but as you can see, that takes time to do that. Where if you were able to obtain the beam pattern simply by electronically tuning the beamformer, you could do it much faster.
Mm-hmm.
And without the drawbacks of cables flexing and such. So that's sort of the reason why we see the MSO as a big advantage for this MIMO testing, because like I said, you could fill out this measurement array with 8 antennas
Mm-hmm.
and measure the beam pattern without having to rotate this.
So
like I was mentioning, we want to be able to make this beam pattern measurement without having to rotate the antenna.
Mm-hmm.
So the problem with that is, and the reason you need many antennas, is these beamformers, as you steer them, the beam pattern is going to change. So you can't really just steer the whole 180 degrees and get a beam pattern. But you can get a really good approximation by not steering the beam very far off your bore site,
Mm-hmm.
but then you have these other antennas off on the side that can do the measurement that would have been done by rotating the whole thing. So you can get a very good approximation of the beam pattern that you would obtain by rotating the whole thing.
Mm-hmm. And that would that would represent this behavior in free space, what we would see outside.
Right.
Great.
So with that, let's just move the beam back and forth a few times just to show that it's real. So right now, like I said, we're steered at the...
But speaking of real, we're going to be able to send live data through this, correct?
Yes, we can. Let's just look at the... just the power for now.
Okay.
So we're at the center antenna, which was the bore site. Now let's steer over to the channel 4, which is the other antenna off to the side.
Okay.
Takes a little while. So now you'll notice that the green trace got much larger and the yellow trace shrunk. So now I've steered the beam over to the other antenna. And go ahead and steer it back again. So this steering is done simply by changing the phase of each of the 4 elements, and what kind of gives the effect of having steered it in the angle where you want it to go, because these signals are arriving at different times. So you want, this one is going to have the signal arrive first. I say arrive or transmit, it's reciprocal, so it could go either way, but I have a better time visualizing a receive than a transmit. So
that's right.
Since it receives this one first, we can delay this line in order to be equal to the one that received it last, if that made sense. So it kind of effectively
changing that plane of front.
Yeah, moves that whole plane. Yeah. So now we should be. Did we steer back? Oh, not yet. Got to push the button. So now we should be back to center.
So what's the big advantage here, the MSO, for this type of work, research?
Well, the big one that I see is for MIMO, because this is ubiquitous now. Everybody is using MIMO. So for some, in the case of millimeter wave, you need it because the waves don't travel very far in air. They don't propagate very well. So you really need to focus that energy where you need it to go.
No one is investing in mechanical turning or gimbals.
No, that would be very undesirable for a cell system. And in fact, in the FR1 band, it's not only used to direct energy, but it's used to increase the capacity of the base stations because now you can steer different beams to different users using the same frequency band without interfering with each other. And I did mention, so we changed the phase in order to direct the antenna, but you can also change the amplitude. They call it amplitude tapering on each of the antennas because these beams are going to form a main beam and they'll have side lobes. And you would like to minimize those side lobes, especially toward a user that you don't want to interfere with. So these algorithms for beam strength, you get pretty complicated. This is a simple 4 antenna array, but they can go all the way up to 256 elements. So when they're doing these algorithm developments with the old-fashioned method, you would have to steer your beam with whatever algorithm that you're trying to achieve and what angle, rotate the whole thing. And then maybe you're experimenting, you want to see what happens to that side lobe, so you do another adjustment, rotate the whole beam again. Or if you had, say 8 antennas out here, you could point to one and instantaneously see what's happening on the other side. So you could do your algorithm development much more efficiently and get that. I think that real-time action is important because you don't want to adjust and then wait a minute to see what your result is. You want to see like right now. So
yeah, that's very clear. Research is showing that the computational complexity for those algorithms to actually wait on something like that to adjust.
So it gives you more of a live tuning capability versus, well, let's try this and then rotate.
In order to keep pace for what is going to basically dominate maintaining service and giving capacity to users in those sectors like you talked about.
Yep. Yeah, so exciting times in the RF world.
Much different than...
this millimeter wave is going to open up a whole new...
right.
I mean, there's applications...
We're no longer tuning PLLs and matching networks. It's computation.
But it's opened up so much bandwidth. There's just going to be... there's apps that haven't been thought of yet, I'm pretty sure.
So tell me, Don, what's the key feature of the MSO that brings value to this experiment and to our end customers?
So the MSO is pretty unique among oscilloscopes in that it has built-in digital down converters. So what this allows you to do is simultaneously see the spectrum and time domain, but not an FFT though. An FFT, you're looking at the same data acquired in the time domain path. So your spectrum settings and your scope settings might conflict and they don't play very well together. This digital down conversion makes it, each channel has a digital down converter, but the down converter itself makes that spectrum and time domain totally independent of each other, which has some big advantages in terms of speed, and like I say, not conflicting settings with each other.
So it's the case that you have independent DSP function on each channel through that digital down conversion?
Yes.
And you could throw out samples as needed in order to decimate?
Right, for the time domain.
I see.
The spectrum domain, though, is going to sample at the full sample rate all the time, and that way, so if you decimate, you're going to reduce your Nyquist rate, so your frequency range is going to follow that. But with the digital down converter, you can keep sampling at full sample rate, so the Nyquist band doesn't change, but you're just going to take a chunk of that and down convert it to IQ.
Okay.
And I say a chunk of that. In the case of the MSO, we're taking 2 gigahertz chunks. So that gives you a 2 gigahertz, what we call real-time bandwidth or analysis bandwidth. That's the bandwidth that you're going to need to demodulate a wideband signal. So you need at least as much analysis bandwidth as the width of your signal. So having 2 gigs is pretty much going to cover most of the signals that are produced today. In fact, more so. I think the highest cellular bandwidth that we've talked about is about 1.2 gig, but certainly that will expand in the future. So each of these 8 channels on the oscilloscope has 2 gigahertz analysis bandwidth capability independently. So each channel can be independently tuned to a different frequency and a different span, different spectrum settings altogether.
So that's enough to meet the needs of FR2, is that correct? The FR2 bands for 5G, 6G?
Oh, yeah, certainly. I think the FR2 bands are up to about 800 meg, but like I said, I think that's only going to grow as more applications come around that need more bandwidth. So that's a couple of the advantages. For what we just talked about, that 8 channels is a big advantage because now you can do this on 8 channels. Where I'm showing 2 antennas here, you could show 8 antennas, which gives you finer resolution on trying to match what you get by rotating.
Agreed, as well as determine the precision of that steering, which is present in that beamforming circuit.
Yeah.
Excellent.
So, you know, like I said earlier too, you don't want to steer the beam very far because it's going to change. So you want to steer it a little and be able to measure with the other antennas. So as these elements get more and more elements, the beam gets narrower and narrower. So you would like to have more antennas to be able to do that measurement. So with one oscilloscope, you could have 8, but you can sync oscilloscopes together to get, you know, sky's the limit, I guess. As many as you could fit in there.
Agreed.
So, yeah.
So that would be valuable to a customer in terms of characterization, in this case of a transmitter. But there also may be some other scenarios which it's necessary to have access to those many channels.
Yeah.
Okay. Don, I'm interested in seeing performance here.
Yeah, let's do some demodulation of actual signals now. So if you remember earlier, I mentioned that we have one signal that's directly connected to the scope from the AWG, and that's the one that we're looking at now. So this is on channel 3 of the oscilloscope, direct from the AWG at 3 gigahertz in this case. So let's demodulate this signal. So here we're showing the signal view software that I mentioned earlier. So this is what's going to turn your oscilloscope into a vector signal analyzer. So I have several measurements up at this point. In the upper left, we have the channel power measurement for that channel. Again, this is a 100 megahertz bandwidth signal, uplink, 10 millisecond packet duration. So the channel power in this case, you can see is about minus 18 or so dBm. And over to the right of that, we have what's called the time overview. So this is pretty much like an amplitude versus time display. But what it's going to show you is the analysis time. So between this window here is the time that we're going to analyze the signal in order to obtain the EVM. And then below that, we have the spectrum display. This is just a normal spectrum. So you can see we have 100 megahertz bandwidth here. You'll also notice some artifacts on the side. These are produced by the AWG, not the scope. For this particular measurement, they don't really matter one way or the other. We can still demodulate the signal. And then over on the left there, or lower left, we're showing the actual constellation of that signal. So I'm going to bump my power up a little bit just before I start railing, because to get the best EVM, you want to be as close to full scale on the A to D as you can get. So I'll back off a little bit here. That's probably close enough. So you can see I got about 0.47% EVM. Already verified this earlier, but that's the limit of this is the AWG, not the scope. With a pristine signal, I've been able to obtain as low as about 0.3% for the same signal. Um, so let's also look at some other measurements that we can do here, in particular the ACLR. And well, before we do that, so we're looking at the direct connect signal now. Let's look at one of the over-the-air signals. So I'm going to go to my scope setting here. You can see I'm connected to channel 3. I believe I left off on the center antenna. Yeah, so that would be channel 1. So let's see what we have there. It's going to be quite a bit smaller signal, so you'll notice the EVM got quite a bit worse, but this is the over-the-air signal now. I'm going to, again, try to get near full scale. I usually try to use the time overview to judge that. As soon as I get to about the top of the screen, that's about full scale to the A to D. And that actually didn't improve the EVM very much, but so I'm going to go back to channel 3. So I want you to notice something here. That's the signal to noise ratio. So the top of the signal to the noise floor here. Looks like we're about 40 dB there. So if I go back to channel 3, which is the direct connect, I'm going to be overranged again. But notice how that signal to noise changes. See, now I got about 50 dB, and hence the improvement in the EVM of the constellation. So just go back to channel 1. Yeah, so you can see that EVM did degrade as you might expect. And it doesn't make a whole lot of difference between full scale and not full scale. And that's because the signal to noise actually got worse from the device, not from the scope. It did get a little bit worse there, but being this far down from full scale, that doesn't surprise me. But yeah, about 1% is about as good as we're going to get no matter what, though. But you can see the reason why is the signal to noise. And of my DUTs here, the weak link is the beamformer itself, which is adding quite a bit of noise. Which makes sense because that's where the power amps are. So now let's do some other 5G NR measurements. In particular, the ACPR, the adjacent channel power ratio, as well as the spectral emissions mask. Okay, now let's take a look at the adjacent channel power measurement. This is that same signal that we measured the EVM on earlier, except it's now been moved to a frequency of 7.026 gigahertz. And the reason for that is you'll remember the spectrum. If you looked at the spectrum on either side of the signal, you see these AWG artifacts. So I wanted to filter those out before showing the measurement here. So I have a filter on the AWG output so that we can get a clean signal coming out of that. You will notice a few spurs in the spectrum, though. These are due to the scope and the highly interleaved nature of the A to Ds in order to achieve those high sample rates. But you also notice, even with the channels that have spurs, they're not a whole lot worse than the ones that don't have any spurs as far as the dBc value of the adjacent channel power measurement. So yeah, here's the adjacent channel power. Looks like we achieve, I'm not quite optimized, but pretty consistent, about 48 dBc from the main signal. So now let's take a look at the SEM. That would be the spectral emissions mask. So I'm going to pause here at this point. Okay, now I've taken that same 7.026 gigahertz signal, and we're going to look at the spectral emissions mask of that signal. And you can see we're looking at 3 different upper and lower sections of that mask. And looks like we're well within range in all the adjacent sections. And now you can see the tabular display of all the outside of the signal measurements here. So that's what we have for the 5G NR analysis. So that would, to summarize, that would be the constellation, the EVM, the channel power, the adjacent channel powers, and the spectral emissions masks. And one other thing, just to show before I let off here, is that so this is what we're looking at now. These are the measurements available, but you'll notice here, this software has many other measurements that you can make. There's also just general signal viewing. We already looked at spectrum, time overview. You have phase and amplitude, frequency versus time. Some general RF measurements, channel power, cumulative distribution function, occupied bandwidth, analog modulations, general purpose digital, pulsed for radar type signals, and all these different standards here. So yeah, this is a long history behind this software here. It has a lot of capability and can really be a powerful addition to your oscilloscope. Well, thanks all. That was the conclusion of this demonstration.
Thank you, Don, for the demo, and Keith for moderating. And hope everyone enjoys the rest of the Tektronix Innovation Forum, and hope you found this demo useful. Thank you very much. Give thanks.